Alright, welcome. We are doing the first homework of a Thermodynamics 1 course. All the solutions on there. The book we're using is Koretsky's Thermodynamics textbook. This first homework is basically covering chapters 1 and 4. Okay, and that's just the way we like to do things. We like to talk about properties and equations of state before we really get into the use of those equations of state within first law and second law analysis. But that's neither here nor there. What is here is what is homework 1, problem 5. We're actually using a Koretsky problem. We're using 1.27, so 1.27. It says, determine the temperature, the quality, the internal energy of 5 kilograms of water in a rigid container of volume 1 at a pressure of 2 bar. So, first thing we do, we draw a picture. Okay, we try to recognize our problem, but really it's draw a picture in this case, because we don't know what kind of problem it is yet. So we're going to draw a picture at least. Okay, so we draw a picture. We write down everything we know. Okay, we know that it's water. We know that the mass is 5 kilograms. We know that the volume is constant and that it's 1 meter cubed. And we know the pressure is 2 bar. But how do we know the volume is constant? We don't actually know. We are assuming it, so we also need to write down our assumptions. Assume that volume is constant. Now, where does that assumption stem from? It stems from that it's a rigid container. So the key word rigid means, okay, it's not going to change, okay? Now, what's the implication of it being constant? Well, there's a couple, but we'll kind of get more into detail on the other implications of constant volume when we get into kind of chapter 2 and such. But right now, and then the last thing we do is we write down our unknowns. Okay? Alright, well, let's see here. There's our problem. Okay. And now we have to figure out what kind of problem is this. Oh, well, this is a steam table problem. How do I know it's a steam table problem? Well, there's steam. Well, there's water. Okay. And it's asking for properties. Okay, so that's a steam table problem. It's asking about water and it's asking about properties. And I have information. Okay. And so, steam table problems, what's the first thing I should do? I should probably go to the steam tables, which is, in the appendix, B1 is where it starts. In Koretsky, that's on page 648. Okay? So, go to my steam table. Next thing I do is I go to either my temperature or my pressure table. Okay. Now, if I'm doing this as a conceptual problem, I don't even have to go to the temperature. I can just go to the, I don't have to go to the pressure, I can go to the temperature, because I can eyeball things. But I am calculating things, so I want to be as exact as possible. So I am going to go to the pressure table. Okay. And I'm going to look up my pressure. Okay. So I look for 2 bar. Now, what is 2 bar? I don't have bars. I have kilopascals and megapascals. So that is 200 kilopascals or 0.2 megapascals. Okay, so I'm looking either for 0.2 or 200, whichever one kind of appears first. It looks like, yeah, I got a 0.2 here. So I got 0.2 megapascals. All right. Okay. The next thing I do is I look at what else do I know. Well, it looks like I know volume. But my table doesn't have total volume. What does my table have? That's right, it has specific volume. Okay. So I need to calculate that. Now, that's just the total volume divided by the mass. And so that's going to equal, in this case, we got 1 meter cubed divided by 5 kilograms. So that is 0.2 meters cubed per kilogram. All right, that's simple enough. So we go down to 0.2 in the megapascals. We go to our volume, and what we're doing is we're looking to see what phase we're in. Are we saturated? Are we subcooled? Or are we superheated? Now, what do I need to do? Well, I need to look, am I within the bounds? Okay, so is my 0.2 within my bounds of liquid and vapor? Let's see here. So according to my table, my liquid is 0.001 approximately, and my vapor is 0.8. Is 0.2 between 0.001 and 0.8? Absolutely. So I'm definitely a saturated mixture. But there's another clue here that tells me I'm a saturated mixture. That's right. I asked about quality. I don't have a quality if I'm not saturated. Okay, so it's kind of obvious. Okay, so I'm at 0.2. I've figured out I'm saturated. Well, now I need to figure out how saturated am I. Am I liquid? Am I all vapor? Am I somewhere in between? Really, I need to calculate my quality. Okay, so I ask myself, am I given the quality or am I calculating the quality? Obviously, in this case, I'm calculating it. I'm given volume, so I need to use the formula to get quality out of volume. And so the quality formula says that V minus V liquid over V vapor minus, well, we'll say gas, because my V's look like L's. V gas, V liquid. Okay. Now, I may need to interpolate, not in this case. So this one I can just kind of plug in my values. Now, for these videos, I'm not going to plug in numbers. I'm not going to plug things in the calculator. I assume you can plug things into a calculator. And if you happen to be fortunate enough to have a code that reads a steam table, what do I want to see? Well, I'll get there. So let's kind of, quote-unquote, calculate these things. Okay, so I have, like I said, I have 0.2 minus 0.001 approximately. And then I have 0.885 minus 0.001. All right, well, that's about 2/9. So it's about 20%. Okay. Okay, so it's about 20%. That's my X. All right. Well, I need my temperature. Well, I'm only given one temperature. Exactly. Temperature, there isn't a liquid and a vapor temperature. They're the same because I'm at equilibrium. Specifically, what kind of equilibrium am I at? I'm at thermal equilibrium, which says the temperatures are the same, whether I'm in the liquid phase or the vapor phase. Because I'm in equilibrium, my temperatures are the same. And so, the other thing is that when I'm saturated, my temperature is dependent upon pressure. It's not independent. So, if I know my pressure, I know my temperature. It's 120.23 degrees Celsius, and I'm good to go. Okay. Last thing is internal energy. Okay. Well, internal energy, okay. Oh, and the other thing that I would want to show here is, I want something like, in terms of the work I want shown, I want like, at saturation and at P equals 0.2 megapascals, VL equals something, V gas equals something, U liquid equals something, and U vapor, gas equals something. Okay, so I do want that shown on your homework. Okay. That way I know you kind of know how to read a table, I know what you're looking for, and more than anything, I know where the numbers are coming from. Okay. I know if you have V gas equals 0.88 and I see down here 0.88, I know that you're putting things in the right spot and not just guessing. Okay, but now we're using the formula for internal energy. Let's kind of erase some of this mess. Okay, now that I have a quantity, now I need to get internal energy. Well, internal energy is equal to internal energy of the gas minus the internal energy of the liquid times quantity plus the internal energy of the liquid. Or here I can use the internal energy of what I think it's, what letters does it use? It uses delta LV. Because that's what delta LV equals, is this. So I can use this also if I want to. Okay. It doesn't matter. Okay, I'm going to plug in those numbers and get something. So 20% between those values. Let's just kind of eyeball things. Okay, so 20%, that's about 400. So I'm going to get about 900 something. You know, maybe 920 or something. Again, you know, the answer is important, but it's not. Okay, it's more, do you understand how the problem works and understand how to get things out of the problem? Now, let's say you have a code that does this, and you wrote that code yourself. Now, obviously, to write that code, you had to understand how to read a steam table. What do I want to see? I want to see the formulas. Okay. I also want to see, okay, used code. Now, you don't need to tell, so I still want you to be able to read the bounds. Okay. And I still want you to write out all the formulas. So this formula, the x equals formula, this formula. Okay, obviously I have to use that to calculate the volume anyways. And then, you know, U liquid equals this, U vapor equals this, so on and so forth. Okay. Now, if you had to interpolate, like the pressure was 0.21, I won't ask you to tell me what U liquid and U vapor is, because you kind of have to do a double interpolation to do that. Okay. But what's important is that, you know, you have all the formulas and you're kind of showing the steps. You're showing that you understand things. Okay. But then at that point, you can just kind of plug in.